do one more electron configuration. This one is going to include the F zone, so we learn how to do the period number -2 when we get into the F zone. All right, so I chose bismuth. Bismuth, if you look at your periodic table, is all the way. I need a better periodic table that you guys can see. Maybe this one's a little better here. Okay, it's not colorful, but maybe you'll see it a little better. Okay, can you guys see bismuth? Here it is, right here. It's in this period over here, period 6. Bismuth, it's over here in group 5A. So we know that it's going to end with P1, 2, 3, P3. It'll be end in P3 because everything in this group ends in P3. All right, so let's start from the beginning. It will be bringing helium over here, 1s2, 2s2, 2p6, 3s2, 3p6, and then here's 4s2. Now that we're in the D zone, remember you go period number -1. So after 4s2 comes 3d10. There are 10 groups of 3d10. And then you're over here. Now it's 4p6. And then come down over here, 5s2. And then 4d10. And then 5p6. And then over here, 6s2. All right, now lanthanum is part of 5d. Okay, so you can go 6s2, 5d1, but now you have to pick up all these f's. So sometimes what I'll do is I'll go 6s2 and then I'll jump over here and go 4f14 and then come back up here and go 5d10. If you want to do 5d1, you can go 5d1, 4f14, and then you have to do 5d9 for the rest of them. And then 6p1, 2, 3, 6p3. So I'm going to write that on the board so that you can all follow along with that and then try to do it yourselves. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, continuing on, 5s2, 4d10, 5p6, and this is where it gets tricky, 6s2. I'm going to go down and pick up the f's, 4f14, 5d10, and then the last one would be 6p3. Now, the alternative, like I told you guys, was you could go 6s2, you could write 6s2, and then 5d1 if you want to just pick up lanthanum, and then get the 4f14, and then go 5d9, the rest of the Ds, and then end it with 6p3. So this is fine, either one is fine. Honestly, maybe Owl has some of the F's, but the Stoker tends not to ask a lot of questions with any of the F zone. Okay, these are tedious. Writing these electron configurations are a real pain. So they've created a really cool shorthand. It's called the noble gas shorthand configuration. What that is that instead of writing all of this, what you can do, so for example, for bismuth is over here. Instead of writing everything, what you do is you go to the noble gas in the period right before. So the period ahead of bismuth would be period 5, and the noble gas is xenon. So what you do, instead of writing all this, I'm going to go ahead and erase it. Instead, you just write xenon. And when you write xenon, that actually accounts for the first 54 electrons of bismuth, because bismuth and xenon share the first 54 electrons in common. They both have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. etc., 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 all the way to the 54th electron. So writing the noble gas, that's a shorthand. It's like a condensed electron configuration where you don't have to start all the way from the beginning. Okay, so then what do you write after that? Then you just continue on. After xenon, what comes next? 6s2, 4f14, 5d10, 6p3. Or you can write xenon, 6s2, 54 electrons, 5d1, 4f14, 5d9, 6p3. This is supposed to be a 6, funny looking 6, 6p3. Okay, either one of these is fine for the condensed noble gas configuration shorthand. Okay, good. All right, so we're done with electron configurations. We're ready to move on to the last topic in this chapter, which deals with orbital diagrams. Remember how I told you at the beginning when I said that the electrons are located in shells and subshells and orbitals. So basically, orbitals are in the subshells and subshells are in the shells. Every subshell has orbitals in it. Each orbital holds a maximum of 2 electrons. So if you're talking about the S subshell, it's going to have just one orbital. Because remember, maximum of 2 electrons. And S can hold a maximum of 2, so it's going to only have 1 orbital. They show an orbital as a line, or as a circle, or as a square. Okay? I tend to use lines. I don't know what, OWL will use, but so if I show a line, you show the electrons as arrows, one arrow going up, one arrow going down, meaning that the electrons spin in opposite directions. They can't spin in the same direction, they have to spin in opposite directions. So in an s orbital, you'll get 2 electrons, always 2 electrons per orbital, and they spin in opposite directions. Okay, remember how we said the p subshell holds 6 electrons, right? So how many orbitals is it going to have? Remember, if only 2 electrons per orbital, so therefore it can potentially have 3 orbitals. But here's the important thing. When you are filling in electrons in orbitals within the same subshell, you have to put the electrons single, single, single before you double up. So basically, each orbital has to have 1 electron in it before any orbital is allowed to have 2. So if you're going to have like a P3, if it's going to end in P3, it would be single, single, single. If it's going to end in P4, it would be single, 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 double. If it's P5, it would be single, 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 double, double. If it's P6, it would be single, 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 and then double, double, double. Get the idea? I think we'll practice. All right, D has how many orbitals? Remember, D has a maximum of 10 electrons, so therefore it would have 5 orbitals, okay? And F, maximum of 14 electrons, it would have 1, 2, 3, 4, 5, 6, 7 orbitals. Again, you're going to go single, 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 and then double, double, double. All right, so let's do an orbital diagram for nitrogen, okay? The first thing you want to do when you're doing an orbital diagram is to first write the electron configuration. Okay, what's the electron configuration of nitrogen? Let's take a look at our periodic table. You see where nitrogen is. So it's going to be 1s2, 2s2, 2p3. So let's write that down. 1s2, 2s2, 2p3. Okay, great. So now let's turn the electron configuration into an orbital diagram. We're going to draw a line. This is 1s. We're going to do the 2 electrons, 1 up, 1 down. 2s, 1 up, 1 down. How many orbitals do we have in the p? 3. So you put all 3 of them. where are the 3 electrons going to go? They're not going to go double, single. Remember what I said, single, single, single before you can double up. Well, we only have 3 electrons, so one's going to come here, one's here, one here. What if we were going to do the orbital diagram for, let's say, fluorine? Let's try the orbital diagram for fluorine. Fluorine. How many electrons does fluorine have? And where is it on the periodic table? Can you see where it is, guys? Fluorine's right here. It's a halogen. It's in group 7A. It's got 9 electrons. So we'll go 1s2, 2s2, 2p5. This whole group ends in p5. So electron configuration, 1s2, 2s2, 2p5. All right, let's do the orbital diagram. Here's the 1s, 2 electrons, 1 up, 1 down. Here's the 2s, 1 up, 1 down. And then you put all 3 2p's. So these are all, that's right, 2p. All these are 2p. And we have 5 electrons. So single, single, single. That's 3. Double, double. There you go. Make sense? One last one. Let's say you have carbon. Carbon is 1s2, 2s2, 2p2. Why is it 2p2? If you look at where carbon is, it's 1, 2, 2p2. That's where it ends. Okay, let's do the orbital diagram. Here's 1s, up, down. Here's 2s, up, down. Now remember, p has 3 orbitals. 1, 2, 3. Where do you put those 2 electrons? Do you put them both in the same orbital? Absolutely not. Single, single. Single, single. So this is called unpaired, unpaired. These are paired. So questions could say, in the orbital diagram of fluorine, how many unpaired electrons are there? You'd have to do the electron configuration, then you'd have to do the orbital diagram, and then you'll see, I have 1 unpaired electron. In the orbital diagram of carbon, how many unpaired electrons are there? This is unpaired and this is unpaired. You know, a pair means 2. So anytime you have an up and down in the same orbital, that's paired. When you have singles by themselves, that's unpaired. Okay, I think we're all set with this what you need to know list, and we're ready to move on to a different chapter. Okay.